Already we have 8.1, using the lock function, comparing it to a constant, which is 3. So what this is saying is that if the lock is less than 3, that will be true. The value coming out of that will be 1, and that the gain will be the gain which multiplies, the gain is 20, which will multiply the output of that and send that to the motors. So then it will send, if that is true, it will send a value of 20 to the motors. If the lock is greater than 3, it will send a 0 through, and then it will be a 0 sent to the motors, and it will stop. Alright, so here we have problem 8.2, very similar to 8.1 where we have the clock, but this time we are incorporating the touch sensor, or the button, so that every time the button is pressed, the rover goes for 3 seconds. So obviously we have 2 inputs, current time and the button. The output is to both motors, which is the speed. Obviously right and left motors, made our own function here. So you can see the output, which is both motors, and then the inputs, current time and button. Our persistent variable is press time. So every time we go through, that sticks, which is when the program is first entered and started. The press time doesn't have any value. If it is empty, the value is equal to 0. That means, so if the button is pressed, then the press time is equal to the current time. And that's the end of that part. But then if the current time is less than the press time plus 3 seconds, then that means that both motors will keep on going until the current time is equal to the press time plus 3 seconds. Otherwise, the speed, or both motors, are equal to 0. Yeah, otherwise both motors are equal to 0. Alrighty, so here we have some similar program to 8.2, but a bit more variable. So here, from the outside, we don't have to go into the function itself to change anything. Still have the clock and touch sensor, so that anytime you touch the button, the program will run. We have the runtime, which is the total number of seconds, and then the set speed. So you don't have to go into the function to change these two. And you'll see in the video later that it's 4 and 40. The robot's going to run for a longer time period and also go faster. And the back half is the same, just more inputs. As you can see, we have 2 extra inputs, runtime and set speed. Still have the press time persistent variable, which starts at 0 when the program is started. If the button is press time equals the current time, which is the time from the clock. And if the current time is less than the press time plus the run time, so that's that 4 that we saw earlier, then both motors will be set to the speed. Once the current time passes that press time and run time, both motors will then be equal to 0 for speed. For 8.4, instead of the clock and running with time, our set thing is distance, or actually almost rotations in this aspect. So, and we're also introducing the encoder block, which tracks the right wheel position, which we have labeled there in the function as one of our inputs. We still have the touch sensor, and we have the travel distance, which is set in the rotations, one rotation being 360 degrees. So 1080 is equal to 3 full rotations, which you'll see later. And the set speed is the same as the last one, where we can change these without having to go into the function itself. And then we also have the display, which shows the position of the right wheel. Again, we have both motors as the output, and it goes out to that. And inside of the function itself, again, we only have the one output, and then we still have the 4 inputs: right wheel position, button, travel distance, and set speed. Remember that travel distance is set in degrees, and the set speed is set like any of our other programs that we've already done. For this program, we also do double the right wheel position, which the blocks naturally do, but we have to do ourselves because it's a user-defined function. Our persistent variable is the mark position in this. It starts out as 0. If the button is pressed, the mark position is equal to the right wheel position, so that's where the encoder comes in. And if the right wheel position is less than the mark position plus the travel distance, then both motors will run at the set speed. Otherwise, if the right wheel position reaches the mark position plus the travel distance, both motors will equal 0. 2, 3. So for this last section, we are using the last block that we have, which is the gyro sensor. One little problem I have here is that we don't have live data going back to Simulink, so I guess I'll have to take my word for it that everything is uploaded to the robot, which is, you can see here, Ethan 5, 8.5, but here we have the gyro sensor, and what it outputs is the rate of rotation. And so that doesn't actually give us how far it's rotated, just at the speed that it's rotating. And so what we must do, we have to double the data type, or for the data type conversion, we have to double it, and then we integrate it, and that will give us the amount that it actually has rotated, because the integral of velocity is then equal to position. And so if it was giving a live thing, it would show up slower and just show which direction it's rotating by negative or positive, I believe, and then how much it is rotated or where it's at.